Alright, we'll start in the next minute or two. Hope you guys had a good weekend. How did the exam go? I didn't see too many, I don't know, questions about things not uploading. I will say it was a kind of a huge pain in the ass to get things from Kudu over to Brew and Learn, and all the grading was like, yeah. I was like, okay, thank God we only have 2 exams. Well, technically I got the final as well, but it's much easier when it's just like in-person paper, because then I just send it through a scanner and we're great. This was me like asking ChatGPT a lot of times, like, how do I format this spreadsheet to go to this spreadsheet so that Canvas likes this spreadsheet? So, and then the other issue is that like on Kudu, some of y'all didn't put in your ID correctly, or you're using different emails. So then I have to ask ChatGPT to try to match the names, but like do a fuzzy match. But yeah, Sophia says it was good. It took a long time, but the difficulty level was good. All right, good, cool. Yeah. I tried to make it like not too difficult. I also don't want to make things too easy. That's the worst. If you're taking a class and everything seems great, and then the final hits, and you're like, "Excuse me, like what was that?" I see these posts on Reddit sometimes. People, they post about professors. They're like, "Yo, what the shit did I just like? What did I just witness, dude? What happened with that final?" So yeah, I want to like gauge expectations. This class will definitely get like a little bit harder. I think we should do like some calculus. It is technically a calculus-based class. If it was the 5 series, then I would like definitely avoid calculus. But y'all are smart. Science, engineering majors. But yeah, took a long time. How long did it take you, Sophia? What, like 2 hours? 3? I designed it to be about like an hour 15, hour and a half, I think. But let me know if not. Because that will be important for the final. The final, I am going to like kind of restrict the timing a little bit more. Probably 3 to be honest. For you, about 3? Okay, cool. Good to know. I mean, yeah, it kind of comes into the like the doubling factor of things, right? Whatever I think it can do, and whatever the TA thinks it can do, it's usually twice for a student. Yeah, okay. All right, well, if that took 3 hours, I guess the final has to be that length. Because the final's only 3 hours long. What's up, Sensation? Dude, what the hell? What Sensation? What is that message, dog? Excuse me? Like some copy pasta from like Gen Z stuff, dude. What the fuck? All right. Amelia says, I'm not gonna lie, it took 3 hours. Okay, cool. Good to know. I'll say real quick, like that type of exam, 8 questions, 2 free response, is pretty close to what I would have to do for an in-person thing for 50 minutes. However, I will say, the in-person exam I did, the questions were a lot easier. And also, the eight multiple choice was like actually multiple choice. This one, we did 4 multiple choice, and then I did 4 like numerical, like I would think like quicker calculations. I hope you recognize that like some of them are literally verbatim questions that we did on the homework or during, I mean, one of the FRQs was pretty close to what we did as a clicker question. I think it was the one with the, like the cube in the whatever. But I understand that the numbers can get annoying, right? Because they're all kind of randomized and like they look weird. The reason why that is, the reason why we have to do that is because it's an online test. The exam would not be as tedious in terms of like numbers changing and like having to like label things if it was in person, because then it would be great. The problem is that like if we use standard numbers and make things easy and then it's across everyone online, it gets very easy to just like pass numbers to each other, and then like I don't know, not calling you out as cheaters, but it's like, you know, precautions we have to take. I really appreciated how you made the content similar to problems we've done before. Nice. Yes, I will never drop something you've never seen before. I think that's kind of cruel and unusual. I may put a twist on it. I may be like, oh, instead of solving this for this, we're going to solve for this. Instead of solving for this, we're going to solve for this. But nothing will be like out of the blue, you've never seen it. I think that's like really mean when teachers do that. what they're kind of going after is seeing if you can apply concepts you've learned to new concepts you haven't seen before, or like a new situation, which is the goal. Like, what we're doing here is trying to teach you the process of taking systems and things that you understand and being able to apply those to new things you don't understand. I just think like doing it on a test is pretty nerve-wracking. So I don't like to do that pressure on students. Everything, like, yeah, you will have seen at some point somehow. Nothing will be like brand new. Like, where did that come from? I mean, maybe like 1 or 2 questions on the multiple choice, but yeah, nothing big. Okay, cool. Yeah. So that being said, we'll start soon here. Grades got released for the midterm. Please email me if you see any like errors or discrepancies. I'm sure something happened. I mean, one student already emailed me like last night at like 1 a.m. right after I posted it, being like, yeah, dude, like my scores showed like 0 for everything. I was like, yeah, you're right. Kudu, for whatever reason, said that like none of his answers got submitted, but he submitted his work, so I was able to see that. I'm like, all right, cool, that matches up, great. Yeah, now you're okay. So if you see any discrepancies with Kudu and what they, because your scores are graded automatically from Kudu, and then we go through on the numerical and the FRQ, and we give like partial credit where we can if like you're, you know, making a good attempt at things. But I don't have time to go through all 100 questions, all 100 submissions, and check, for instance, if like your part C would have been right with part B if like you had used a different number or used the same number or whatever. So for that, you can send me an email and be like, you know, hey, Dr. Gold, like I looked at the solutions. It looks like my answer for part B, you know, was correct, and C got marked wrong, but it really was just like a really, really tiny math error. That's okay. Send me an email. I'm sure we can give you a couple more points here and there. And you've been doing a good job so far, the emails I've gotten, but make sure to put the time in to like explain why. Don't just send me an email being like, I think I deserve more points here, and then that's it. Explain to me why you think you deserve more points. And it helps if you like send screenshots like explaining why. Sensation, dude, what? Dude, Sensation, do you have a fucking bot now like hitting my chat up? Dude, Sensation, chill. Or is this really you talking? Okay. Problem is, like, Sensation is a mod in my YouTube, so if his account got compromised and it's just spamming chat, it's I. Okay, good. All right. Well, yeah, just yeah. Do that during Twitch, Sensation. You can do whatever the fuck you want. Spam the chat during Twitch, but all right. Here, let's start off. We're gonna. Sorry, dude. Okay, thanks, Sensation. You're okay. You can do whatever the fuck you want on Twitch. Spam all the chat you want there. Just leave the YouTube for the kids so that I can teach them. All right, let's see. Welcome. All right, let me turn the lo-fi music off. Yeah, my bad. I forgot that last time. Welcome to week 4, lecture 1. Nice. So, yeah, this week we're going to finish up some cool things with electric potential, and then we're going to get a little bit into circuits, it looks like. And then I think eventually the following week, week 5, we're going to round it out with like capacitors and things, and like some more detailed circuit stuff. But yeah, this week, very important, these first 2 days, we're going to go over electric potential. And what we're going to start with is electric potential energy. This usually isn't like used in E&M. We honestly don't really care about this electric potential. We care about potential. Potential energy is just adding another Q is all it really is. But a lot of times what we're really going to deal with is electric potential, and this is called like voltage. But all of them together, this is equal to Q times V. This is called like energy of like a system. Yeah. This is the simplification is what it is. Okay, but before I get into electric potential and electric potential energy, let's try to think about some other potential energies we know, right? So other examples in physics so far that we've dealt with like potential energy. So, for instance, one potential energy you know is gravitational, right? So we got gravitational. So if we had, for instance, a block right here, right? It's chilling on the ground. And we say here that gravitational potential energy is equal to 0. And then we take that block and we move it up a height h, okay? This now has a potential energy which is equal to mgh. We did this in mechanics, right? Okay. A similar thing happened with a spring, okay? Right? So this was gravitational potential. Then we also had like spring potential. Okay, so here we go. So let's say, for instance, we had a spring here that was attached, right? And then we moved it a distance x. Okay, let's say we moved it like from its equilibrium, right? Let's call it like delta x. Here, right, we say like UE is equal to 0, like right here. But at this point, we end up saying that UE is equal to 1/2 kx squared. And these are things you just learn, right? We just learn like, oh, this is what potential energy is. The real like definition for how potential energy works is the amount of energy that is stored that could be converted into kinetic, right? So for instance, we know right here, right, that this block, when it's raised to height h, doesn't want to be here, right? It wants to be down on the ground. And so this is energy that can easily be converted into kinetic to drop it down. Same thing here with the spring. If the spring is stretched out, like it's pulled and stretched out, it wants to be back at equilibrium. And so that's energy that could get converted really easily into kinetic if we let it go. So how I like to think about potential energy is you're doing, in storing energy in potential, you're having to do work against a field, okay? So, for instance, with gravitational, right, the field there is gravity, right? So here we have like F is equal to mg. In terms of the spring, right, what you're having to fight is equal, is the spring potential energy, sorry, the spring force, and that's F is equal to 1/2, not 1/2, sorry, F is equal to kx, right? And this one, right, this is pointing to the left, so this is like, you know, trying to restore it to here. This is trying to restore it here. Okay, so what you can think about if you wanted to say like, okay, let's talk about like potential energy. That's equal to the work you put like against a field, or you can see it as the negative work done by a field, right? So if you're doing work on an object, right, against a field, that's the same thing as the negative work being done by the field on the object. This is also assuming everything is like moving at constant velocity, right? There's no like acceleration. Okay. And you learn this as well, right? Like, you know, W net, changing Ke stuff. Okay. So for the gravitational one, right? So the negative work done by gravity, right? That's going to be equal to the force of gravity, which is equal to mg, times the distance. And in this case, mg, right, is like pointing down. Distance is pulling, is force of gravity is pointing down. Distance is pointing up. So the potential energy there is equal to mgd. Same thing as mgh. Or actually, sorry, this is equal to, yeah, negative work done by the field. One sec, let me make sure this is right. Right. Yeah. Because these things are opposite. So this would be the double negative happens, right? Okay. if we look at it this way, right? This is, let me, the signs are important. Here we go. Okay. So it's equal to like negative, and then this would be like negative mg times d, because they're in different directions, so then these cancel. You get mgd, and that's mgh. So this is where like potential energy from gravity comes from, right? Or U grav. Let's just say U grav equals mgh. Okay, let's look at the spring, for instance, okay? So with the spring, when you try to like take something from where it's at zero potential to like some non-zero potential, the spring force, right, is fighting that distance to the left. If you wanted to do just like W equals FD, you can't really, because the force is not constant, right? Because we know that F is proportional to the distance, it's proportional to X. So what we end up having to do here is, in order to find the work done by the spring force, right? That's going to be equal to the integral, right, from a position 0 to a position delta x of f dx. And the force done by the spring, right, that's pointing to the left, that's kx. So you get 0 to x, 0 to delta x, and this is going to be like negative kx dx, which, integrating this is a simple integral, right? You just raise the power, divide by the new power. This gets you negative 1/2 kx squared, and then that's evaluated from 0 to delta x. And so that's the work done by the spring. But remember that the potential energy is equal to the negative work done by the field. And so we say, like, U spring is now equal to 1/2 kx squared. Okay? So that's where spring potential energy comes from. You're really just integrating the work done by the field as you bring it from zero potential to somewhere else. I think also, yeah, we also call this is technically called like change in potential energy, because it's how much work is being done to bring something from somewhere to somewhere else. But in both cases, I'm having my initial position have a defined potential energy of 0. Yeah. Okay. I know that's maybe a little bit a lot. Does this make sense so far in the mechanics sense? How we define like potentials in terms of work being done by fields, or the negative work being done by fields to bring them from like zero potential out to some like non-zero potential. Like basically like a place where they're chilling and they're at equilibrium to a place where they don't want to be and they would like to convert that into kinetic. That's the main point I want to get across here. Because it's gonna start playing into charges. We're using like Coulomb stuff. So, yeah, let's see. I'll give people a couple seconds. Totally cool. All right, yeah, the signs, yeah. All right, so negative work done by the field. So if we, yeah, let me get this done. Let me like fix this. Okay, let's just calculate work done by gravity, and then we'll put the negative on it. So work done by gravity is going to be the force of gravity times the distance, right? This is the classic work equals force times distance. Gravity points down to something moving up, right? If I'm moving something from the ground anywhere above the ground, then my distance is going to be opposite to the direction of my force of gravity. And because those are opposite, that's going to give you a negative sign on the work. So this is going to be negative mg times d, which in this case, if its distance is now h, right? So we would say that the work done by gravity is equal to negative mgd. So then the change in the potential energy due to gravity is equal to negative mgh. Sorry. So that's just equal to mgh. You can think about it as like the force you would have to apply to get something somewhere, or it's the negative force done by the field. They're both the same. Yeah. Okay, cool. All right. So let's extend this framework we've come up for potential energy, and let's do it with Coulomb stuff. Okay. So now, potential energy due to charges. So let's say, for instance, I have a positive charge here, Q1, right? Okay. And I want to figure out the potential energy of the system if I have another charge out here, let's say Q2, which is negative, okay? Again, we know that this charge here will radiate out an electric field, which means that field has a force associated with it, right? Actually, sorry, let's make this one positive as well. Let's not do the negative case. That's going to confuse people. We'll do the negative next. Okay. Sorry. We'll make this positive. Okay. This is going to radiate out an electric field, right? And we know that this Coulomb force will try to push this thing away. So what should make sense here, right, is that as I try to bring this thing closer, it doesn't want to be here, right? These two fight each other. They repel. So as I bring a charge closer to here, I am increasing the potential energy of the system because it would like to be, like, you know, shot off away from it. And that would convert stationary potential energy here into kinetic energy way out here. Right? The further away this is from this, the less force it feels. So what we end up saying is that if Q2 was way out at R equals infinity, like super far away from this, okay, then its potential energy, let's say like Coulomb potential energy, would be equal to 0, right? There's no potential if this thing is super far away. It doesn't even feel this charge. It doesn't even know where it is. It's just like, you're too far from me. It's long distance relationship. It doesn't work. But as I bring this thing in, okay, closer to here. So let's say, for instance, I bring it here. Some distance, let's say like R, okay? Now, I have had to exert a force. I've had to, like, input work to do this. And the field, right, has done negative work on this object to bring it from here to here. So let's look here. Let's say, okay, what's the work done by the electric field? Well, that would be equal to the force of the electric field, right, times the distance. But the force here is not constant with distance, right? Because we know that the Coulomb force goes as 1 over r squared. So what we say here is that, okay, well, this is K, Q1, Q2 over r squared, right? This is the Coulomb force. And we're going to have to integrate that, right? Over some dx. But so here, this is the Coulomb force of the field, which points away from dx. Dx is pointing this way. We're trying to bring something from here closer into here. The force points that way. The force is the Coulomb force is opposing this. So we end up putting a negative here, right? And then where are we integrating from? Okay. Well, my starting position is no longer 0, right? Here we define potential energy when the height was 0. Potential energy is when the spring stretchiness is 0, when it's at its equilibrium point. Here, the equilibrium point, when this thing has 0 potential, that's when it is infinitely far away. So we end up putting an infinity here. Okay? Yes, dx are infinitesimally small steps towards q1. Yes, so as I bring this thing closer and closer to q1, I need to add up what the force was acting on that charge as I brought it a little bit more dx closer and closer. Nice. And eventually I want to bring it all the way out from infinity to some position r. Yeah, so let's do that. Okay. And so here I'm gonna replace this with x because x is r basically, right? We're doing this in one dimension. Okay, so now let's integrate. So this is gonna be negative k q1 q2 integral from infinity to r, and that's gonna be 1 over x squared dx. All right, this is a pretty basic integral. This is the same thing as x to the negative 1 dx, which, you know, raise the power divided by the new power. Or, sorry, x to the negative 2 dx. Sorry, I wrote that wrong. Negative 2 raised becomes negative 1 divided by negative 1. So we're going to get negative k q1 q2, and then that's going to be... all these negative signs get pretty annoying. But there's a negative, and then it's 1 over x, and then that's evaluated from infinity to r. Okay. So, okay, now if we do this, right? So that's going to be negative k, q1, q2, negative 1 over r minus 1 over infinity. Right, because there's a minus, there's another minus there. That's plus. So then you get, the work done by the electric field. That's when it's from 0, right? Yeah, 1 second. Let me make sure we do this. 0 to this. These minus signs are tricky to deal with. Ugh. QQ, that points away. Mm-hmm. Okay. You're going to get k q1 q2 over r, and that's equal to the potential energy in the system, but I got another negative on it. I don't like the other negative. They put a minus there. That's like the work done by us. Positive work. Oh. Oh, wait, 1 second, 1 second. Yeah, no, it's R1 minus R2. But then there should be another minus sign, yeah. Yes. Yeah, good. Yes, sensation, don't worry. They're students. They already hit the like button. They're okay. Appreciate that, though. Sib says, can you explain why we're going from infinity to R? Is that because we're evaluating, we're saying that the potential energy here, way out at infinity, is 0. And that's when R is equal to infinity. And then we're bringing it into a distance R, which I have a minus sign wrong somewhere. 1 sec. This one, we brought it from 0 to that. The force was... Oh, wait, whoa. This is opposite. Oh, I see. Oh, I think I have this flipped. That's negative. That makes sense. Oh, no. 0 to delta x. forces to the left, right. Yep, cool. Yeah, this makes sense. Why is this one flipped? Mm-hmm. Okay. Well, ends up being potential energy here. Let me go through this during office hours. There's a minus sign somewhere, but this is the correct answer. I wanted to say it's the negative force done by, it's the negative work done by the field, but now it's like it's the positive work done by the field. I feel like the field should have been doing negative work. The force and the distance. Oh, no. Okay. No. Yes. All right, I know where I'm screwing up. Sorry. Okay. Sorry, this is dr. Ha! Sorry, no, this is right. Okay, so what's happening here, this is actually kind of cool, is that dr, let's remember that dr, that points from the center here. This is 0, right? So dr actually points in this direction. Dr points away from the origin, right? So in this case, the force and dr are pointing in the same direction. Okay, got it. I was bugging for a second here. I'm just like, yo, excuse me, what? Yeah. Yeah. It matters here. Okay, so watch. Let me see. Okay, so here, for instance, dx was pointing in this direction, right? Because this was x equals 0, and this was x equals a positive number, right? And so f was pointing in this direction, so f and dx are opposing each other. Here, however, we are bringing it from outside in. We are bringing it in this direction, but that means dr is going from a positive number to a low number, right? It's going from something that's very far away, because dr is measured from the origin, to something that's not so far away. So in this case, dr is negative, right? Dr is going from a very big number, infinity, all the way to like just r. So this is negative, this is negative. Or no, sorry, these are in the same direction, right? And that makes these are both positive. And so then when I take the integral, I pop out a negative. Okay. And now that would get me this. So this is the work done by the electric field. But potential energy due to the electric field is equal to the negative work done by the field. And so that's going to equal to K Q1, Q2 over R. Nice. Okay, cool. Got it. Okay, there we go. So this is the potential energy of having just two charges, Q1 and Q2, next to each other, separated by a distance R. Okay? Yeah, this is the calculus part that tends to sometimes confuse people. You have to keep track of like all the different directions and like where things are going and like, is this positive? Is this negative? Yeah. Yeah. The important thing is that like R hat points away from here. So, this kind of shows us that, yeah, we're going from like this. That's gonna make it. I got it. Okay. Cool. So yeah, dr and force are pointing in the same direction. However, we are stepping dr backwards from infinity to r, and that's why eventually we end up getting a negative number here, because we're going like backwards. Let me see if people remember this from like integration. If you have a line like this, okay, this is AB, right? And let's say this is like f of x. The integral of f of x from a to b dx is equal to the negative integral of f of x dx from b to a. So if you go in the direction of dx with your bounds from a to b, you get a positive number. But if you go from b to a, such that you're opposite to like where dx points, this whole thing will be negative, and so you need another negative here to equal what the original thing is, because it's the same area. This has to be positive area. If you traverse adding up your area in the direction of dx, you get a positive area. If you traverse in the opposite direction, you're going to get a negative number, so you have to put another negative out front in order for there to be a positive area. Okay, cool. Sorry, I just want to be... I hate when, like, professors, like, just do... And then they just wave their hands. They're just like, yeah, don't worry about it, don't worry about it, don't worry about it. I'm like, no. I want to point out, like, the math of, like, why that negative sign comes out. Okay. Let's do a clicker question. I think there's a clicker question related to this one. Okay. Okay. There's that. Oh, I need the answers. Okay, here we go. It says, consider an unknown charge that is released from rest at a particular location in an electric field so that it has some initial electric potential energy. In what direction will the charge move in regards to its potential energy? Okay. So let's remember the example we had here. Okay. So we're saying that a charge is placed in some sort of electric field such that it has positive potential. So in that case, we could think about, right, that I have positive charges here, right? And I have an unknown charge, let's say U, that's pointing here, and it has positive potential, okay? Which means that it doesn't want to be there, right? The electric field that would be produced by this, right, would mean that you would have to have other negative charges here, right, in order to create some sort of field. So remember, when we have like positive charges and negative charges next to each other, that creates a field. So this would be the field, which is E. Okay. And another thing we learned, right, is that the force on a charge is equal to QE. Okay. So it depends on what the charge is. So let's think about this. We know, right, that if something has positive potential here in an electric field, then that means getting closer to here would increase the potential energy if this was positive. So we say, like, if U was positive, then moving to the right is more potential energy. I shouldn't have called... I called it U because it was unknown. All right, let's just call it like X, sorry. Because U is potential energy. We run out of letters in this class. Okay. If X is positive, okay, and it has positive potential here, right, then moving to the left would mean you would have more potential energy. Yes, it is why Greek exists. I just didn't want to, like, start putting more things. What's up, Aditya? Good to see you. Okay. If X is negative, okay, now moving to the left is less potential energy, right? Because if this was negative, this thing wants to go here anyways, right? And pulling it away from here is like pulling it away from something that's like fighting it. Oh, you had an exam? Oh, it's okay, Fedekai. Hope your exam went well. We have office hours later today, Fedekai, at 3. So in like an hour 50 minutes. This is the physics class I teach. Okay. So if this thing is positive, right, then this is more potential. And then this is less potential. And so it said, let's see what we see. Both positive and negative charges can move towards either higher or lower potential energy. Well, that's false, right? Things tend to move away from high potential. In the same way, sorry. Sorry. I mean to say potential energy. Everything we're dealing with here is potential energy. We will deal with potential tomorrow. Sorry. The way they're related, I'm just so used to saying potential because that's all we really deal with in E&M. We don't really deal with potential energy. But potential energy is the same thing as QV. So this is potential energy. And then this is electric potential. I know, it's confusing sometimes because you're like, bro, what? Why? And also U and V look kind of the same, depending on like how curved your stuff is. You all have a lot of potential. That is true. Yes. Okay. This is electric potential energy. Electric potential energy is this, and this ends up being electric potential. And this is like a charge. We say this is like, we call this like a test charge, or a test charge in some potential creates a potential energy. We'll get into potential tomorrow. Okay, so sorry. A charge will not move either towards higher or lower potential energy. Charges like to move away from being at high potential energies. In the same way here, right? With the mass, right? With gravity. It has higher potential energy when it's higher up in the air. It doesn't start moving even higher, right? If you let go of it. It wants to go down to lower potential energies. It wants to go to 0. The same thing here. If you have a block that is on a spring that is stretched out, that is at high potential energy. It doesn't want to be there. Nature loves things to be at low potential energies. Like we say, this is like organized, like lowest energy states. Nature is a sloth. It loves things just being like really chill. It loves just Netflix, whatever, on the couch. It doesn't like to be in like strenuous situations. So that's another case of where the block will move towards a lower potential energy. In the case of the charges, if I have a positive charge here, which is at a higher potential energy. Remember, we defined potential energy equal to K Q1, Q2 over R. So if this is small, then your potential energy is big. It doesn't want to be here. It wants to move away towards lower potential energies. In the same case, if this was a negative charge, right, it being further away is not desired because it wants to be closer to here because these things attract each other. So that's a case where I didn't do the negative charge case because I don't want to confuse people yet. But with negative charges, it turns out like as you get further away, you have negative potential energy because it actually doesn't cost you any work to bring something that's negative in from here. Because this thing is trying to pull it in anyways. It's the same thing with the block here. If you try to like move the block down, you're not increasing the potential energy. You're decreasing the potential energy because you're doing things in the same direction that the force wants to put it. So in this case, yeah, this one is wrong. Yeah, they don't move towards either one. And really what we say here is that like a charge will move to regions of lower potential energy regardless of positive or negative charge. Yeah. It doesn't matter what the charge is. It wants to move towards lower potential energies. If this was a positive charge, right? Moving to the left would mean increasing the potential energy because you're moving it against where it wants to go. If it was a negative charge, right? Moving it to the left would decrease electric potential energy, because you're moving it away from where it doesn't want to go. Where you're moving it in the direction it wants to go. It wants to get away from negative charges here. Ben says, can you clarify how the direction of integration affects the sign of the result physically? I thought integrating forward or backwards isn't the same as moving the charge in that direction. It is. Yeah, no, you're talking about here when we go from infinity to R. That's the same thing as moving it, again, from like some location B to some location A. That's the same thing here. So if this was infinity and then this was R, then the integral from like infinity to R is equal to the negative infinity from negative integral from R to infinity. Yeah, cool. Yeah, you're good. All right. Let's see why the other ones weren't right. A charge will move to regions of higher potential energy regardless of whether it's positive. That's the same answer. What? Oh, sorry. I read this wrong. Higher potential energy. Yeah, no. Things don't want to move to higher potential energies. You have to put in work to do that. Is this why the particle in a box stays inside the box? Yeah, that's a good example. Yeah, that's called a what do they call that? Stable equilibrium. For instance, yeah, it's the same thing as kind of like, yeah, stable equilibrium. Right? If you have I always love relating things back to mechanics, but if for instance you have a ball, right? That's chilling here, yeah? If you try to like raise the potential, so this is like higher potential, it doesn't want to be there. It will try to restore down to its lowest potential. So yeah, when something's in a box, a particle's in a box, it doesn't want to be outside the box. You have to put energy into the system in order to do that. You have to fight the field. Here you're like fighting gravity. I think in quantum mechanics, yeah, you talk about like you're fighting a potential well. Like you can kind of always like try to visualize again as like gravity, but in that case, I forget. Like I think the potential can be anything. It can be like electroweak forces, strong nuclear forces. There's a bunch of like weird quantum forces that can like keep things in places. But yeah, so this one's wrong. Stuff does not like to move to higher potential energies. A negative charge will move to regions of lower potential energy, but a positive charge will move to regions of higher potential energy. Yeah, no. Doesn't matter if it's positive or negative. It always wants to move away from the force that's fighting it. And because that's how we define electric potential energy. Yeah. Okay, so answer choice there is A. I'm spending a lot of time on this because this is something that is commonly mistaught. It's commonly misunderstood, and then everyone starts screwing up the minus signs later in life. And so I really, really want to like reiterate, get it into your heads like how it works. Okay, cool. That one's good. Okay, so now we're gonna talk about like potential energies of some charged systems here. Okay, cool. Okay, so here we're asking about rank the potential energies of the four systems of particles shown below. Okay, so previously, right, we found the electric potential energy of having what's in the box, yeah, of having a charge here, Q1 that's positive, and then bringing another charge Q2 here was positive, yeah. So this is what we did is we calculated basically the work that would be required in order to bring this into here. That's another way to think about calculating the potential energy of a system, is how much work do you have to do to make this system? Right? With the gravity, we have to do mgh to bring the block up to h. with the spring, I have to do 1/2 kx squared to bring the block, stretched out on the spring. With a series of charges here, so you always get a freebie on the first charge. So, for instance, to build this system, they don't have either. Okay, whatever. We'll say it's this one. To build this one, right? The first thing you would have to do is to bring a minus Q charge from like wherever and put it there. But that required no work to do that, right? There was no work done by any field in order to bring this initial minus Q1, this minus Q charge here, right? Because there is no electric field. It's just vacuum. However, the second I place this negative Q1 charge here, okay, now there is an electric field being created by that charge. And that electric field is what is going to repel me bringing in another minus Q charge next to it. And so the work required to bring this minus Q charge in, which is the same thing as the negative work done by the electric field, that is the electric potential energy. So you always get a freebie with this. But then bringing in a friend, right, bringing in this one, that's where you actually have to do work, and that's where you're creating electric potential energy in the system. Having just a single charge here and nothing else is a totally cool situation. There's no strain on the system. Like, the minus Q charge can just chill here. But the second I bring another minus Q charge next to it, now there's some, like, tension. And that's electric potential energy. What we found from earlier, right, was that for just two charges, right, Q1 and Q2, the electric potential energy was equal to K Q1 Q2 over R. Okay? So this is a good thing we learned just for two charges. So we said, okay, cool. For two charges, potential energy is equal to K Q1 Q2 over R. So now I have a bunch of two charge systems here. I just need to figure out what the potential energy is for everything, right? So, looking at this one, right? So for A, that would be like plus Q plus 2Q over R. Don't worry about the K. The K is the same everywhere, right? So that would end up being like 2Q squared over R. For B, you have minus Q over R. So this is the same thing as Q squared over R. So already A has more potential energy than B. Now let's go for C. C is a plus Q and a minus Q over 2R. So this ends up being minus Q squared over 2R. Notice this is negative potential. The reason being is it does not take you very much energy to bring a negative charge close to a positive charge, because the positive charge wants the negative charge to be there. You're not putting in any energy into the potential energy here by bringing a minus charge. Like, that was already wanted. That's free. Well, it's better than free. It's you're getting paid for it, honestly. Like, if you want to think about, yeah, like maybe some sort of like metaphor to it, right? Usually it costs money to bring something else in, right? But if something is already wanted, then they pay you for it. Yeah. Okay. So that's why this is negative potential. Okay, and then for D, we have minus Q minus 2Q over 2R. So that's going to be 2Q squared over 2R. So that's equal to Q squared over R. Okay, cool. Yeah. So it would be negative work. Correct, right? Think about the work done by the field there is actually, in this case, ends up being positive, right? Because, listen, the field from this is trying to pull this thing in, and the distance it's moving is also in that direction, right? So that's why you end up getting like negative potential. Yeah. Yeah, no matter the charge, things always want to move to regions of less potential energy. It's the same reason that masses always want to run to the ground and stretched out springs always want to go to their equilibrium position. Charges don't like being stressed. They want to be, in this case, if you have a positive and a positive, they want to be as far away as they can. If it's a positive and a negative, okay, now this thing wants to be as close as it is to here, right? Because pulling a negative away from a positive is putting stress on the system. It's like stretching the spring out, right? The negative charge wants to be close to the positive one. Yeah. Okay. So looking at this, I see that B and D, these are the same, right? And this is the most, like the most positive. And then this is the least, which is technically the most negative, but yeah. So, what is that? A is greater than B equals D, which is greater than C? Yes, yeah, potential energy, yeah. Yeah. Yeah, so you have to be careful interchanging the words potential and potential energy, okay? Because technically an area of a bunch of negative charges is negative potential. Right? Okay? But it depends on like what charge you have next to it, right? So if you have a negative charge here, right? Moving towards like negative potential is technically an increase in electric potential energy. The reason, and we're going to get to this, is that potential energy is equal to QV, where this is defined as like the charge in the potential. And this is the electric potential energy. And then we're eventually going to learn that this is equal to KQ over R. And so this is the potential created by a point charge. So if you have a single negative charge, that creates a negative potential, because potential is KQ over R. But then, depending what charge is next to it, determines what the electric potential energy is, right? So if you have a positive charge here, okay, now you have negative electric potential energy, because it takes you negative work to bring a positive charge out from infinity close to the negative charge. It wants to be there anyways. If this is negative, okay, then you have negative Q and then a negative potential. That creates a positive electric potential energy, because it takes work in order to take a negative charge all the way from infinity and bring it close to another negative charge. We're going to get into potential tomorrow. I'm just doing potential energy today. Yeah. Okay, so this should be A, B equals D, and then whatever, C. Oh, so what answer choice was that? Sorry. That was answer choice... Answer choice A. Okay, cool. So let's see if that's correct. Cool. Good. Okay. Okay. Oh, we do have to go through electron volts. Okay, I got 15 minutes. I can do it. All right, let's do it. Right. And then also, so this was simple cases for, again, just constructing two charges. If you wanted to find the electric potential energy, for example, for 4 charges, this ends up like really sucking. What you have to do is you have to calculate the work required to bring in each one of these charges. So you get the first one you can bring in for free. Doesn't take any work, so there's no work needed. But then as you bring, like, let's say for instance you bring the first one in, you have to consider the work done between these two. Now, if you bring in this charge while these two are here, you have to consider the forces done from these two charges on this. So then there's like two separate works. And then finally, when you bring in the last charge, now you have all three charges, which are going to make it difficult for you to bring in that fourth charge. And so, yeah, you end up calculating like the work to bring in this one, which is just due to this, the work to bring this one, which is equal to the opposing forces from this, and then the work to bring in this one, which is the opposing forces from all three. And then you add that all together. It takes a lot of time. Maybe it's a homework question. But okay. Right, so the thing we learned is that, yeah, electric potential energy is going to be equal to Q times V. And then, so here, let me just, okay, so electric potential energy is equal to Q. So this is the charge. And then V is like in a potential. Okay. And then what we can do is this can get measured in a bunch of things. Electric potential energy is usually measured in joules. But we can also measure this in what's called electron volts. So like 1 electron volt is equal to a charge, we say like E. So this is 1.6 times 10 to the negative 19 coulombs times 1 volt, which is potential. And so the way they define the electron volt is it's the amount of energy moving an electron down 1 volt of potential. I will explain this more tomorrow. I'll explain more like what potential is compared to potential energy. But for now, just trust me with this, is that as you have charges moving, you know, around in what we call the potential created by a charge, that creates a changing electric potential energy. So for instance, when the charge was way out here, your electric potential energy was 0. But then when we brought it in, right, we increased the electric potential energy. And how we did that is we took a charge Q and we moved it across a electric potential created by this single charge. What we end up doing later is we think about what the electric potential is created by a bunch of different charges. In the same way that we considered what the electric field was created by a bunch of different charges, individual charges create their own electric potentials that make it either like difficult or easy for other charges to like move closer towards them or away from them. In the same way that like electric fields work. But yeah, just to do this clicker question, we have to just define this real quick, which is electric potential energy is charge times the potential that it's in. And a lot of times you'll be given the potential. You'll be told that, like, for instance, right, volts, you probably see this, right? This is the same thing as like batteries, right? Like batteries can create voltages, which are like regions of potential, which when you move charges in potentials, you have changing electric potential energy. In the same way that when this charge is moved around in the potential created by this charge, that creates changes in electric potential energy. Okay. So let's see if we can do question 3 real quick. I will explain more of this tomorrow. I thought we would get through to this, but it took me a little bit more time to explain electric potential energy than I thought it was going to today, which is okay. Okay, so it says an electron is accelerated in a uniform electric field having a strength of 2 times 10 to the 6 volts per meter. Okay, this is an electric field, right? So we say E is equal to 2 times 10 to the 6 volts per meter. If the electron starts at rest and it is accelerated through a distance of 0.277 meters, what is the electron's final kinetic energy? Actually, I think we can just use work energy here. The issue is that they put it in electron volts, and I had to explain like how electron volts work. Okay, so let's say well, okay, an electric field is pointing this way. If electric field's pointing this way, this is like plus and this is minus. And then if we have an electron has a negative charge. So this is going to be the electron. And let's say it starts at rest, okay? We know that this thing is going to want to move this way, right? And that the rate at which it moves there is going to be dependent on like the acceleration. And the acceleration there is dependent on a force by F equals ma. So, we can think about this. So, remember that like the net work done on an object is equal to the change in the kinetic energy. This is work energy theorem from kinematics. So, the net work done on an object is equal to the force times the distance. And then this is going to have to equal the change in kinetic energy. Which, if it starts at rest, right? So we can say 1/2 mv final squared minus 1/2 m v initial squared, but that's going to be 0. Okay, cool. So let's think about the force. So we learned from last week that the force on a charge is equal to QE. So in this case, that's going to be negative E. E is like the charge of an electron. So like Q for an electron is equal to like little e. Okay, so negative E times the electric field, which is big E, and then the distance it travels. So it's traveling 0.277 meters, but that's also in the same direction, right? That's also to the left. That's negative because it's moving towards the positive charge. So the force, which is equal to QE, right? If E points this way but Q is negative, the force is going to pull it this way, but also the direction is that way. So the work is going to be positive. So this will be like negative 0.277. And here, let's put in values here for the electric field. Electric field is 2 times 10 to the 6 volts per meter. And then this is also in meters. And what do they want? Oh, they just want kinetic energy. Oh, okay, so we actually don't even need this. I thought we needed the velocity. We don't care about the velocity. Sorry. This is just going to be like KE final minus KE initial. But we say it starts at rest, right? So this is equal to 0. Okay, cool. Should see something interesting here, right? Look, meters is going to cancel out with meters. And I'm just going to have E, which is like the charge of an electron, times volts. So you end up getting negative point... Well, the negatives are going to cancel, right? So I'm going to get 0.277 times 2 times 10 to the 6. And then that's going to be electron volts. Because E in this case, I know it's part of the unit. E is the charge of an electron. Which is technically 1.6 times 10 to the negative 19 coulombs. And this is also why like 1 electron volt is equal to 1.6 times 10 to the negative 19 joules per coulomb is also what they say. Or sorry, just joules, sorry, that's what I meant to say. Yeah, it's similar to equals IV. Well, yes. Yeah. Okay. So then if you multiply these two things together, let me get my calculator up. 0.277 times 2 e to the 6. We're getting a lot. 554,000. So 554,123. Okay, and that's electron volts. So that's equal to 554 kilo electron volts, right? Kilo. This means like 1,000. Let's just see. What were our answer choices for this one? Yes. So that's gonna be answer choice A. Now you could have done this using just coulombs and everything. If you wanted to, for instance, say like, right, F D is equal to delta KE, and then F is equal to QE D equals delta KE, and then if you did 1.6 times 10 to the negative 19, and then you did is this 2 times 10 to the 6, and then you did 0.277 is equal to delta KE, you would have gotten a different number, but this would be in joules. Okay? And then you'd have to do the conversion, which is 1 joule is, or 1 EV is 1.6 times 10 to the negative 19 joules. So what you end up doing is you end up dividing by this anyways. So watch what happens. If I do this, let's just do this. Let's do this real quick, right? So 1.6 e to the negative 19 times 2 e to the 6 times 0.277. That gets you 8.86 times 10 to the minus 14 joules. Okay? Because that's energy. Energy is always in joules, right? But then you can multiply that by, 1.6 times 10 to the negative 19 joules is 1 EV. And watch what happens if you divide this. 1.6 e to the negative 19. You get the same answer. You see how you get the exact same answer there? You still get 4,000 electron volts. So yeah, you didn't need E. You could be smart, and here when you have like F is equal to, right, QE, you could leave this Q as E, and then just notice that like, oh, well, E and V is electron volts, and then you just have to multiply these two numbers, and you already have your answer. Or you could do it out in coulombs if you want. This is volts per meter. This was meters. You'll get joules, and then you can do this conversion, and you'll also get the same answer. Just two different ways to do it. Okay. Okay. I wanted to do question 4 because now you'd be actually calculating the velocity. So before here, when we did this question here, we only calculated what the change in the kinetic energy is. But we know the change in kinetic energy is also equal to the change in 1/2 mv squared. So if you know what this is and you know the mass of your thing, you can also figure out how fast the electron is now going. And so that's what we would have gone through in question 4. No, I'm running out of time. Well, okay, let me do it real quick. It'll take like 2 seconds, I think. The reason why this is cool is this is a CRT. Maybe you guys aren't old enough to know what CRTs are, because, I don't know, maybe you probably didn't even have CRTs growing up. But we used to create, like, things on the television by taking an electron here, and we would rocket it towards a screen, and that would cause light to form on the screen. And then you'll learn when we do magnetism is that you can also create electric fields here or magnetic fields in order to like bend them in different places. And that's how you would create the image, by bouncing electrons at different parts of the screen. But okay, so in this case, they say an electron starts from rest and is accelerated across a voltage of 1,000 volts. Calculate the speed of the electron when it strikes. Well, that's pretty easy, right? So we say that QV, which is equal to the electric potential energy, has to equal 1/2 mv squared. Because you're going from all electrical potential energy to then going to kinetic energy. So, what's that? So that's E. Well, okay, we need everything in terms of joules because we have meters per second here. So this would be 1.6 times 10 to the negative 19. That's negative Q, right? Your change in your voltage is now negative 1,000 volts because you're going across a voltage difference of 1,000 volts. And so then this equals 1/2. And then this is the mass of an electron times V squared. So you can just solve for this. So let's do... I'll explain this one during office hours if you want. I'm just going to go quickly through what the answer is. Okay, times 2. Mass of an electron. Oh, man, it's something times 10 to the minus 34. 1 sec. No, 10 to the 9 times 10 to the minus 31. Okay. Okay, cool. That's very big, and then you square root it. And cool. We get 1.88 something, so that's going to be this one, right? This is very close to the speed of light, right? Everyone remember the speed of light's 3 times 10 to the 8th? So you can get electrons almost up to the speed of light just putting them through a 1,000 volt potential difference. But okay, so that should be answer choice A. Let's go do that one real quick. Answer choice A. Nice. All correct. Cool. Awesome. Okay. Thank you, everyone, for coming to today's lecture. Sorry, I went a little bit over time. There's a lot of concepts here, and I just really want to make sure you understand these. Like, potential is the one thing I remember as an undergrad just got kind of like glossed over, and it really screwed me for like the rest of my life. Until now. Like, now that I teach it, now I understand it. So I really wanted to make sure you guys understand potential. If you don't, like if you're still lost with what's going on, that's okay. You saw it for the first time today. We went over it in like an hour and 15 minutes or so. Please, again, come by office hours, ask any questions about it. I'm happy to like dig into it and really make sure it clicks for you. But okay. Yeah. Make sure pre-lectures, right, are due on Tuesday. Please do those pre-lectures. Your homework for whatever is due today at 2 p.m. And we'll have class same time, regular tomorrow. Okay? Cool. All right, I'll let you guys go. Enjoy the rest of your Monday. Good start to your week. And we will have office hours in about an hour, 10 minutes. So come on by then if you want to get some additional help. And yes, please email me about your exams, and we'll do regrade requests.